Dear student, I am Rupak Shah from the Millennium School, South City, Lucknow. Today I will be taking your lecture number 2 for magnetism. And before I start today's content, there is a small recap of the content that you've studied in the last lecture. Dear students, please follow. The magnetic field lines that you have made for the bar magnet look like this. Please follow something that when we draw the magnetic field lines for bar magnet, it looks like this, and I told you these lines are called closed curves and they are symmetrical on both sides, and there are some properties that we also discussed that I would like to bring to your notice. Once again, the lines move from north to south pole. If you see the direction, already I've told you that when we make a magnetic field lines, these lines are moving generally from north to south pole. Almost this is possible for all the magnets or all the electromagnets. We'll be discussing about the electromagnets and the permanent magnet in this video also. But I just want to say that all the magnetic field lines move from north to south pole. Also, we told you that lines are closer at the poles and they are farther at the center. What does this mean? This means that your magnetic field is strength is very strong at the poles and they are weaker at the center. So this point the magnetic field will be strong, and at this point the center or middle portion the magnetic field is weaker. We also discussed that lines never intersect each other. Because why we see that lines are not intersecting each other? Because there is only one and only one direction from the compass possible from this, or you can say that only unique direction is shown by the compass needle, which will never match each other, and as a result these lines cannot intersect each other. So I have given the justification that magnetic compass shows one and only one direction from one given point or one point. So I hope these properties are quite clear to you, and please observe all the videos carefully so that none of the content are not understandable by you. You can also give any queries to us so that any problem can be tackled easily. So now we are moving to the symbol and SI unit of magnetic field. Already I told you the region or area all around the magnet is called magnetic field, where the magnetic force can be felt, and it is given by the symbol capital B. It means whenever we are using this magnetic field is given by the symbol capital B, and the SI unit of the magnetic field will be Tesla. It is given by symbol capital T. So now we are moving to the difference between permanent magnet and a temporary magnet. In the last lecture, we are told that we make an electromagnet by passing the electricity. And those magnets where the electricity, or we can say the most magnets which work only when the electricity is passed to them, that's called electromagnet. But there are some permanent magnets also. Whenever we'll get time, we'll tell you the construction of permanent magnet also. But the permanent magnet do not need electricity for their working. So they are not called electromagnet. So I am taking one by one the points where you must note down the difference. The magnet made by the electricity and loses magnetism whenever the electricity is switched off. It means it is working as long as electricity is given, and as soon as the electricity is withdrawn, they will not work. But permanent magnet on the other hand, they do not depend on the electricity. So they are permanent magnet, but they don't need any electricity to work. Now electromagnet, the poles can be changed or reversed. In the electromagnet, we can make the north pole south pole, and we can make south pole and north pole. It means we can change the direction of the magnet, or you can say poles of the magnet, by changing the terminals of battery cell which is connected to it. But in the permanent magnet, the poles cannot be changed, they are fixed. North will remain north and south will remain south as long as it is there a permanent magnet. Strength can be increased or decreased by the electricity. Again, your temporary magnet or a electromagnet which is working on the electricity, which is called temporary magnet, their strength can be increased by increasing the electricity or decreasing the electricity. But on the other hand, your permanent magnet, the strength is fixed, they cannot be changed. And generally the temporary magnet or electromagnet is made up of soft iron, but your permanent magnets are made up of alloy called alnico or nippermag. I will give you the more compositions of the alloy that we normally take for making permanent magnet at the later part of this video, but you must be clear about the difference between the electromagnet, which is basically called temporary magnet, and a permanent magnet, which is not an electromagnet. So there are some compositions of the permanent magnet. Normally we see they are made up of the alloys called alnico. Already I have told you in the last lecture, alnico stands for aluminium, Ni stands for nickel, Co stands for cobalt. So it is an alloy of aluminium, nickel and cobalt with some amount of iron. Similarly, nippermag can be used, carbon steel can be used, tungsten steel can be used, or we can say the steel is an alloy itself. So that is normally used for making the permanent magnet. I hope the composition of the permanent magnet is also clear to you. So today we'll be taking a very important topic that is called electromagnetism of various types. In the last video, we have told you that electromagnetism is caused by electricity, or you can say the magnetism is caused by electricity. And I told you the experiment for Oersted also, that whenever we pass electricity through the straight conductor, it becomes a magnet, and more precisely they can call the electromagnet. So one by one we'll take the electromagnetism in each cases. First, straight current carrying conductor. Second, circular loop or a coil carrying current. And third is solenoid. Today we will be discussing only about the rules of electromagnetisms and straight current carrying conductor. Circular loop and solenoid will be discussed in the next video. So let's take a rule for electromagnetism. You can see this picture. This is a right hand that I have hold like this. So this is the thumb and these are the folded fingers. So you can do like this. So this is something like that. Thumb and the folded fingers. So this is the straight conductor that we are holding, and in this straight conductor the current is moving up. So this thumb is showing the direction of current and folded finger is showing the field lines. So according to the rule, if you hold the straight conductor like this and the current is going up, so your folded finger, which is pointing towards anti-clockwise direction, will show the field lines. You can see here also that current is going up and your field lines which are made is showing the anti-clockwise direction. So if it is reverse, for example, if it is reverse, if the current is going down, your field lines will go in clockwise direction. So how will you define the rule? According to the Maxwell right hand thumb rule. This is the rule taken for electromagnetism, showing the direction of current and magnetic field lines. Maxwell right hand thumb rule. According to Maxwell right hand thumb rule, if you hold the current carrying straight conductor on your right hand, thumb shows the direction of current and folded finger shows the direction of magnetic field lines. I'm sorry. If I is up, it means the direction of current is up. I already told you the field lines will be anti-clockwise. If the current is down, the field lines will be clockwise. So these rules are very, very important. So this rule that I am saying is showing you that rule is called Maxwell right hand thumb rule. So in this rule, we are holding a straight conductor and the straight conductor is going in this way. So current is moving up and your folded fingers are pointing in anti-clockwise direction, or you can say all the circular lines which are made or the field lines which are made are showing the anti-clockwise direction, But on the other hand, if you take the current, your anti-field lines will go clockwise. We'll give you example how you to make this field line, how to use this rule in the next topic. That is the the electromagnetism in straight current carrying conductor. This is the experiment normally we do. This is the cardboard, and we are passing a straight conductor AB from the center, and we are drawing a magnetic field lines after connecting it with the help of cell or battery, switch and a rheostat. This is the rheostat for increasing or decreasing the current. So dear student, please understand this diagram. Clearly see this diagram. This is the straight conductor AB which is passed through the you can say a cardboard which is placed like this horizontally, and your straight conductor is passing vertically from it. So the current direction as per flows from plus to minus. This is going down. So if the current is going down, you can easily see that if you apply the rule, current is not, you can say the current is going down. So if the current is going down, my fingers are rotating in clockwise direction. So you can say the field lines are clockwise and current is going down as per the example taken in this. So we get a concentric circles as a field line. So when we draw the circle, these circles are concentric circle. What do you mean by concentric circle? Concentric circles are the circle having the common center. So these field lines look like a concentric circles having a common center at the point which I am marking here. And your magnetic field will depend upon two factors. One factor is current and second factor is distance from the center. Since it is depending on the current, so it is directly proportional, and since all forces decreases with the distance, so similarly you can say as we increase the distance from the center, your magnetic field will go on decreasing. So if your distance increases, magnetic field decreases. It is inversely proportional. So we can say if the current increases, B increases, B means magnetic field increases. If R increases, it is reverse, the magnetic field will decrease, inversely proportional. So you can say with the distance, as we move from the center, your magnetic field goes on decreasing. So it's my suggestion to see the video at least for 2 or 3 times, follow them clearly. Next time I will be discussing this thing again in details, and if you have any query, I told you are free to contact me and clear your doubts. Okay, thank you so much for today. Next time I am going to take you for the circular loops and solenoid. Thank you so much.